Hello everyone and welcome back. Today we're going to be talking about another variety of differential equation called an exact equation. So we're going to determine what makes a differential equation exact, and then we're going to show how to find an implicit solution to an exact equation. So implicit solution is just referring to a solution which has not yet been fully solved for y. And when I say solved for y, in particular, I mean algebraically. For example, some implicit solutions may have the form something like x squared plus y squared equals 4. This describes a relationship that must be satisfied by a quantity called x and a quantity called y, but it doesn't have y isolated. Another example might be something like y plus 1 over y minus 1 equals x. It would be possible to algebraically solve this for y by clearing fractions and rearranging and whatnot, but that has not yet been done. And so this would be another example of what's called an implicit solution. Now, one thing about implicit solutions is that even though they may not already be written in the form function of xy equals c, all of them can be written in that format. All your x's and y's on the left side and a constant on the right side. The example given in the first line is already in that format. The function is x squared plus y squared, the constant is 4. We can also rewrite the second example in that format by subtracting x from both sides. Now we have a function of x and y on the left and the constant 0 on the right. So all implicit functions / implicit solutions can be expressed in the form some function containing x and y is equal to some constant. Now, writing solutions implicitly is most natural when you're working with a differential equation which is in differential form, because it's easy to check whether an implicit function is a solution to a differential equation in differential form. And that's captured by the following theorem. If the function f of xy equals c describes an implicit solution to the differential equation in differential form mxy times dx plus nxy times dy equals 0, then the following property must be satisfied by the function f of xy. If you take the partial derivative with respect to x of this function f of xy in the implicit solution, then that's going to be the same thing as the m of xy, which is next to the dx. And if you take the partial derivative of the function on the left side of the implicit solution, then that's the same thing as this function n of xy, which is multiplied by dy. So this can be used to check if a given function is a solution to a differential equation in differential form, but we're really going to be using it backward. We're going to use the theorem above to take a differential equation in differential form and construct an implicit solution. We're going to use this theorem to solve differential equations in differential forms. Now, when is it possible to use that theorem to find an implicit solution to a differential equation in differential form? It's possible when your differential equation has a property which is called exactness. Under what circumstances is a differential equation quote-unquote exact? It's exact under the following circumstances. If you take the function m of xy, which is multiplied by dx, and you take its derivative with respect to y, and if you take the function which is multiplied by dy and you take its partial derivative with respect to x, if those two mixed partials are equal, then we say that the differential equation is exact. Hopefully this is beginning to remind you a little bit of something that you encountered in Calc 4 when you worked with vector fields. When we had vector fields, in particular two-dimensional vector fields, with some function in the first component and some function in the second component, the vector field was said to be conservative if the partial derivative with respect to y of the x component was equal to the partial derivative of the y component with respect to x, if those two mixed partials were equal. So this is very, very similar to that. We take the mxy, which is multiplied by dx, take its partial with respect to y, and take the nxy, which is next to the dy, and take its partial with respect to x. If those are equal, the differential equation is said to be exact. So let's do a quick check. Let's determine whether or not each of the following differential equations is exact. And in the first example, our function m of xy, which is being multiplied by dx, is given by the quantity 2x plus y. The function n of xy, which is multiplied by dy, is given by negative x plus 6y. Now if I take the partial derivative of m with respect to y, take the partial derivative of the x function with respect to y, then I get the number positive 1. But if I take the derivative of the n function, the function on dy with respect to x, then I get minus 1. So these two numbers are not equal, and as a result, this differential equation is not exact. What about in the second example? In the second example, the function which is being multiplied by dx is given by 5x plus 4y. The function which is multiplied by dy is given by 4x minus 8y cubed. So if I take the partial derivative of m with respect to y, then I get the constant multiple 4. And if I take the constant multiple of the y function with respect to x, then I also get the constant multiple 4. So these two functions are equal, and as a result, the differential equation is exact. Now back in Calculus 4, when a vector field was conservative, there was a function which was called the potential function for that vector field. And it was used to do things like calculate line integrals using the fundamental theorem of line integrals. And in this situation as well, when we have an exact differential equation, we can find a quote-unquote potential function. But in this context, the potential function is going to be an implicit solution to the differential equation. If we have an exact equation, m of xy dx plus n of xy dy, then there is an implicit solution which has the form f of xy equals constant, which satisfies that the partial derivative with respect to x of the implicit solution is equal to the function multiplied by dx, and the partial derivative of the solution is equal to the y component n of xy. So, if we want to find the implicit solution f of xy, all we have to do is partially integrate the functions m and n, exactly the same way that we did in Calc 4 when we were finding potential functions. So in case you need to review that process, let's go through it slowly here. Let's solve the exact differential equation 5x plus 4y dx plus 4x minus 8y cubed dy. Okay, So the first thing that I'm going to note is that this implicit solution that I'm trying to find satisfies the partial derivative with respect to x of the function f is going to be equal to the function 5x plus 4y that is forming the x component of this differential equation. So in order to undo that, I'm going to take, in a sense, a partial integral with respect to x, treating y as a constant. So 5x becomes 5 over 2x squared, 4y becomes 4xy, and then plus c. But because y is being treated as a constant, this plus c term may contain some y's. So I'm just going to denote this as c sub 1 of y. Now simultaneously, we know that the implicit solution's partial derivative with respect to y must be equal to the y component of this differential equation, 4x minus 8y cubed. So the solution itself on the left side must be equal to the integral of 4x minus 8y cubed with respect to y. So let's integrate that, treating x as a constant, 4x times y minus 2y to the 4th power plus c, but this plus c might contain some x's because this time the x's are being treated as constants. Now both of these expressions, the one in green and the one in blue, are representations of the exact same function. Our goal is really just to make them match. And the key is really in the c sub 2 of x and c sub 1 of y. This term, which is a match to this term, 5 over 2x squared, which contains numbers and x's. This term, which contains numbers and y's, is a match to the negative 2y to the 4th, which contains numbers and y's. And then the two mixed terms match up exactly. 4xy is a match to 4xy. So by putting these two representations of f of xy together, we get that f of xy must be equal to the mixed term plus the y term plus the x term, which was 5 over 2x squared. And therefore our implicit solutions to this ODE are given by 4xy minus 2y to the 4th power plus 5 over 2x squared is equal to some unknown constant. It would be, in theory, I guess, possible to take this equation and isolate y to get an explicit solution. But because of this y and y to the 4th power, that seems like it's going to be a huge pain. So we can leave this solution in implicit format. For practice, let's give it one more try. Let's solve the differential equation. This monstrosity times dx is equal to this monstrosity times dy. First, let's check if it is exact. Let's check if it's quote-unquote conservative in the language of vector fields. Now, before we can check whether it's exact, we should make sure that the differential equation is written in accurate differential form. And differential form requires that both the mxy dx and the nxy dy are on the left side of the equation and 0 is on the right side, which is not true presently. So let's go ahead and make that adjustment. Let's subtract 3xy squared plus 2y cos x dy. And now we have equals 0. So if we take the function which is multiplied by dx and the function which is multiplied by dy, we can now check whether or not the differential equation is exact. Now, while you're doing this process, be careful not to mix this up with the process of actually finding an implicit solution. When we check exactness, we take partial derivatives. We take derivatives, and there's a sort of mixiness between the variables. We take the derivative of the x part of the differential equation with respect to the other variable y. And we get, looks like negative 3y squared plus 2y sine x. When we're checking whether the differential equation is exact, we take derivatives of, in this case, n, the y component, with respect to the other variable x. So taking the derivative with respect to x, we get negative 3y squared, and cos becomes negative sine, which cancels with the minus sign outside. So these two partial derivatives are equal, which means that the function is exact, which means that it is possible to find an implicit solution using the method outlined in the previous example. Now that we have determined that the differential equation is exact, we now begin a different process. Instead of taking the derivative of m with respect to y, we take the integral of m with respect to x, almost completely opposite. So our function m was given by x minus y cubed plus y squared sine x. Which is equal to x squared over 2 minus xy squared, y squared cos x negative, plus a constant term that may have some y's in it. Oh, whoops, typo up here, folks. This one's definitely supposed to be a y cubed in m, and this one should also be a y cubed. Integrate n with respect to its corresponding variable, integrate n with respect to y. Basically the complete opposite of what we did when we were checking for exactness. If I integrate this with respect to y, then I get negative xy cubed, and then integrate the second term with respect to y, and we get negative y squared cosine x plus some term that contains numbers and x's. So now let's go ahead and try and match this up. The two terms which contain both x's and y's are already identical in both representations. Here's the term that contains only x's and constants, called c2 of x in the bottom representation, called x squared over 2 in the top representation. And in the top representation we have c1 of y, but there is no corresponding y's only term in the bottom integral, so c1 of y is just going to be empty. So putting these two representations together, our implicit function left side, our implicit function is given by negative xy cubed minus y squared cosine x. The x term is x squared over 2, and there is no term containing only y's. And as a result, our implicit solutions to the ODE have the form negative xy cubed minus y squared cos x plus x squared over 2 equals some constant. Again, it would, I guess, theoretically be possible to take this and isolate y to get an explicit solution, but it's just not going to be worth the effort. In cases when you're solving exact equations, having solutions which are implicit are perfectly acceptable. That concludes today's material. We talked about a special kind of ODE in differential form, which was called an exact equation. They were basically the equivalents of conservative vector fields from Calc 4. Exact equations had solutions which were written in implicit form. The implicit form solutions were basically the equivalent of the potential functions for a vector field in Calc 4.